Welcome to the Energy Technology Selection by Greg, Blaze, and Sebastian. All right, let's get into it. So,
For the intro criteria, we talked about each of the different factors that could play a role in the energy selection. And each of these we weighted with a particular importance. So as you can see from the values, we have different areas of focus and different levels of importance for each of them. We considered the social structures required as one of the least important things because policy can always follow changes towards better technology, even if policy doesn't keep up usually. And we recorded sustainability as one of the most important levels, as we are currently in an energy crisis, sustainability crisis, climate crisis, whatever you want to call it. We have a lot of value placed on the sustainability of whatever energy source we're using. Everything else kind of fills in the middle. Reliability and cost are quite important. Cost kind of drives the economic practices, and reliability is very important to maintain people's power at all times, which is something the consumer has become used to.
so true. All right. So I researched the hydroelectric power. So basically, hydroelectric power, it uses flowing water with a dam and channels the water through turbines, which then transform potential energy into electricity. Different types of turbines can be employed, primarily determined by the head of the plant and other factors such as efficiency and cavitation. And the world's top five largest capacity power stations all operate on hydroelectric power. And then on a smaller scale, hydroelectric power can provide power to smaller buildings with a running water source nearby, and they would only need a water diversion system, a turbine slash pump, and a generator to do so. Now then, for the cost criteria, when you're building the hydroelectric power plant, for a large one, you're going to be paying about $1,050 to $7,650 per kilowatt of power produced. And on a smaller scale, it goes up a little bit, $1,300 to $8,000 per kilowatt. But there's a pretty low maintenance cost and a long life for all the parts on the power plant. And a typical lifetime for these plants is about 100 years, which is pretty good. And the maintenance costs per year are about 1.5 to 2.5% of the original investment, which is not that bad. In terms of the efficiency, they have hydroelectric power plants have an efficiency of about 90% when converting the potential energy of the water into electricity, which is the highest efficiency of any energy source. One of the components that contributes heavily to the efficiency of hydroelectric plants is the use of pumped storage, where basically the reservoir of the pumped storage functions like a battery, which stores energy in the form of water, and then during periods of low demand, and then it generates maximum power during daily and seasonal peak periods. And one benefit of the pump storage is the ability of hydroelectric generating units to initiate quickly and make swift adjustments in output. For the scalability of these guys, it's pretty good because they account for the top five largest systems, but they can also be scaled anywhere in the middle and all the way down to like a little tiny one, which could just provide power for like a shack or something near a river. The sustainability of these, they are pretty sustainable. The only fuel that's used is the water to turn the turbines, which is entirely renewable due to the water cycle, which is powered by the sun. One negative effect is that when human-made reservoirs are constructed for hydropower facilities, they change the way carbon is emitted and stored in the river systems, which sequesters some carbon. Yeah. And there's also some concerns regarding wildlife and how it's affected by the plant. For the reliability, they're pretty reliable. Essentially, as long as the water's going, electricity is being produced, and the machinery used to harvest the power is built to be super reliable and lasts a long time, and outages are super rare. So that is pretty good for reliability. In terms of safety, generally they're pretty safe, but sometimes, such as in the incident of the dam failure in China, 171,000 people were killed, um, which is not great. But it doesn't happen that often if you build them good. And the current rate we've got is 138,175 terawatts per depth, which, that's not too bad. Uh, Human impacts. There are both positive and negative impacts on people that result from hydroelectric power being installed. Some of the positive ones are that dams provide irrigation for different types of agriculture and can help with food mitigation. The reservoirs are then often used for recreational purposes, which is pretty nice. But some negative impacts are that the space for the installation of the plants can cause the displacement of people in the area, and the construction of dams has been used to oppress people in unstable regions of the world. Um, Overall, typically, the social structures, the people have a pretty good view on hydroelectric due to its minimal negative impacts on the environment and its outstanding efficiency. Uh, and if the area around the hydroelectric plant is carefully taken into account, there's typically no issue with affecting the ecosystem. However, in some third world countries, the use of damming can be used to exploit the less fortunate, which could lead to a negative image of hydroelectric power for those people. But that wraps up hydroelectric, and I'll toss it on over to Blaze.
All right, so wind turbines are essentially hydroelectric power, but with air as the medium. So getting right into it with costs, it's basically technology has advanced significantly in this industry in the last like 10 or 20 years, and the price has been significantly reduced. As of 2021, the price per kilowatt was 800 to 950, but you also need to consider maintenance, and so 1 to 2 cents per kilowatt hour produced. Each wind turbine costs about 42 to 48 grand in maintenance per year on average, and that's going to vary based on different locations, weather, and those sorts of things. So wind turbine efficiency, real quick, I just want to say that efficiency isn't that relevant for wind turbines because it doesn't really matter if you don't use all of the kinetic energy of the air to generate, like it just doesn't really affect anything. It's not like burning coal or something like that, where it's like you still have the fossil fuels and that coal could have been burned for something else. But efficiency of turning the kinetic energy of air into electricity is 20 to 40% at best. That being said, larger turbines are more efficient. And so efficiency is reduced by several factors, including lower wind speeds, changing directions, and of course, turbulence. All right, scalability. So scaling is pretty straightforward when it comes to wind turbines. It just means more turbines. And this is possible, but it requires a large open area. And so that kind of contradicts my third point, which is it's best if it's close to a civilization because energy is lost in transport of electricity. But this has been done and is currently done all over the world, but it's not extremely common. And so one of the other reasons it's not extremely common is of course, that the production is limited by the wind at any given time. And that is that's a factor we'll get into on reliability, but varying wind direction can be combated by facing the different turbines in different directions. But that's just, of course, going to mean that at any given time, they're all not going to be at the perfect right direction of the wind. Sustainability. All right. So, of course, wind is renewable energy. The only carbon production is in the manufacturing, transportation, and installation of these turbines. And one thing to get out of the way is that birds are killed because of wind turbines. And right now, it's estimated that 140,000 to 680,000 birds are killed each year. It's kind of brutal, but there have been recent developments where it's like if you paint the end of one of the blades, then the birds stop flying into them. But anyway, that's something that should be considered, as birds will often cross like huge swaths of land. You don't want to just like wipe out an endangered species. And also wind turbines require a large amount of steel, and steel is 97% iron, and iron mining is famously requires huge energy inputs and is usually highly toxic to the environment. Reliability. All right. This is one of the biggest concerns for wind power. So on average, March and April are the windiest months, with July and August being the least windy. This is on a nationwide level, but that's obviously different in different regions. And then there's also the issue that there's no real reliable long-term wind prediction. There's just too many factors and variables involved. And of course, as I mentioned earlier, they require yearly maintenance. And so one solution to this reliability issue is if you have like large batteries to store excess energy on like the windy days, you could possibly supplement this with solar, and maybe you'd be covered all the way. All right, safety. There's not a huge safety concern with wind turbines. The only real concern for human life is during maintenance. And of course, it's just because these are inherently huge structures that can be a hazard to service. But only about 100 people die per trillion kilowatt hours, which is pretty good. And after the raw materials have been acquired, it's relatively one of the safer technologies. Human impacts. Okay. So the price for consumers isn't very high, as it's only about 1 to 2 cents per kilowatt hour. But it's pretty costly to create one of those huge production farms. And there is a potential to one of the good human impacts is there's the possibility that you could bring cheaper energy to more people, and pretty much everyone benefits from that, not just the people directly. So that's great. Social structures. So usually wind turbines are supposed to be certified. Their design is supposed to be certified before building. And also, yeah, they're typically built from government subsidies, i.e. taxpayer dollars. And so one of the issues is figuring out an ethical and equitable way to distribute and follow through with subsidies would be and is crucial because like money is money, but it's difficult to get equitable and ethical access to the people that should get it. And as I mentioned earlier, most people are just happy to have cheaper and cleaner energy. So with that, wrapping up wind turbines, I'll pass it to Sebastian.
Okay, so the power source that I looked at was the thorium power plant, or specifically the liquid fluoride thorium reactor, call that a lifter for short. Harnesses nuclear fission, not a fusion reactor, and heats a molten salt that powers a typical Brayton cycle usually, with helium, nitrogen, or carbon dioxide as a working gas. It could be incredibly small, with powering only 2 megawatts thermal, up to 1 gigawatt thermal, and possibly even larger. Many different countries are creating plans to build these kinds of reactors, with China and India most notable. And China is actually the one that plans to build the 1 gigawatt plant. They're far safer and more versatile than uranium-based plants and are the key to more sustainable nuclear power. For the typical 100 megawatt size reactor, costs are estimated to be 2,000 to 4,000 kilowatt electrical, with an initial investment of $200 million per unit. These are pretty cheap costs, and the reason to do this is because of the ability to produce these units on an assembly line. The reactors themselves operate at atmospheric pressure. They're not pressurized at all, and they don't need any kind of emergency cooling because they're passively cooled. We'll get to that more in the safety section. The reactors also last for a very long time and need relatively little maintenance. They're designed to last around 80 to 100 years, depending on the model. And the maintenance that they need is generally to replace the external components, such as the turbine or the compressor, that aren't necessarily core to the nuclear reactor itself and can be replaced pretty easily and cheaply. Lifter plants are the most efficient nuclear plants to date. A very specific 198 megawatt thermal design that was being looked at by NASA has a thermal efficiency as high as 50.5% for the total plant, which is way higher than the 30 to 33% plant efficiencies achieved by classical nuclear plant designs, and even the 45% efficiencies achieved by modern nuclear plants. This is because of the very high turbine inlet temperature of 1200 Kelvin, and the nature of the helium working fluid, which is often the most efficient working fluid out of the three possible. This model actually, interestingly enough, had no reheat and instead only had intercool technology in the Brayton cycle, which was much higher efficiency than the option that did have reheat and multiple turbines. The lifter plants can be scaled to deliver different power ranges, as can be seen from the production of the Chinese Sinap group. They aim to produce 2 megawatt thermal, 10 megawatt thermal, 100 megawatt thermal, and 1 gigawatt thermal units by 2035. And they're going to begin construction of commercialized versions later in 2035. The mechanics of the design change very little depending on the output of the reactor core. But for the mass production and ease of efficiency, the 100 megawatt thermal design seems to be the most popular international choice, backed up by India and even the United States design. Still, the footprint is pretty small, so you can build a bunch of them next to each other, and the Indian government is planning to build 19 such reactors in Gujarat by 2030. Lifter reactors are among the most sustainable nuclear reactors in existence. This is because they depend on thorium fuel instead of uranium, which is several hundred times more abundant than the U-235 in the Earth's crust. Thorium doesn't need to be enriched because it's fertile instead of fissile, meaning that the uranium itself, the thorium itself, rather than being distilled down to some specific isotope that needs to react, such as U-235, it instead can just be used in bulk. It also produces significantly less nuclear waste by volume, about 300 times less, and what it does produce is significantly less radioactive and toxic. The waste is 83% spent in 10 years and below background radiation levels in 300, which is miles better than what we're dealing with now. Lifter plants are incredibly reliable, like all nuclear plants. They can operate with passive safety systems for years, even completely unmanned. Obviously not recommended, but possible. They barely need maintenance since the cores are not pressurized or actively cooled. There's very little mechanical processes going on that actually need to be maintained inside the reactor core itself. They run at peak efficiency pretty much indefinitely with a steady supply of fuels. Once again, passive. There are no conditions beyond an emergency that would reduce their operating efficiency, like in the case of wind or water power. there's basically no reason the nuclear power plant would ever stop. And even in the event of an emergency, the plants are extremely robust, and once they're drained properly, as can be seen in the safety section, they can begin operation again very quickly. Obviously, safety is the biggest concern when you hear the words nuclear power. Lifters have blown this concept out of the water. They're completely unpressurized and aren't actively cooled, so you won't have any accidents like Chernobyl or 3 Mile Island. They don't deal with steam. They deal instead with helium, which basically makes, this whole negative void coefficient problem from Chernobyl impossible. They aren't immune to meltdown because the fuel inside the core is already a molten liquid. There is no meltdown possible, and the entire reactor is designed to contain this molten liquid already. They also employ passive safety systems instead of active cooling. So if the power ever fails and there's no one present to deal with it, the reactor will still regulate itself in a safe method. The reactor itself has a freeze plug at the bottom that is actively cooled and will only stay solid as long as it is powered and as long as the controller deems it necessary. So if anything ever happens, the freeze plug will go out first. If the power goes out or if someone, presses the emergency panic button, the freeze plug will melt away, and all of the fuel will be drained out into a tank stored deep underground that allows you to safely store the contaminated fuel or whatever the problem is until the tank can be drained at a later date. Additionally, thorium is not fissile without the plutonium component stored above the reactor. So as the salt fuel is drained away, it is taken away from its fissile component and cannot run away in any kind of further reaction. The biggest question regarding human impacts when considering nuclear power is inevitably safety related once again. The locational safety component has been pretty much addressed. There's not very many environmental dangers from the reactor. So all that remains to deal with is the weaponization concern. Fortunately, thorium plants can't be weaponized. Non-proliferation is guaranteed since the amount of plutonium contained in one reactor is far too small, orders of magnitude too small to create a bomb. And thorium is not fissile, so it can't be weaponized any more than any other metal could. Additionally, thorium is much safer to mine. It doesn't produce any of the toxic gases that uranium does. So the mining process for uranium is actually incredibly dangerous. Not a lot of people know this, but thorium doesn't suffer from any of those problems and is much safer to work with in pretty much every way. The main issues standing in the way of lefter technology are centered around social structures. People just don't like nuclear power at all. And even those heavily in favor of the environment and sustainable energy are usually opposed to nuclear solutions. A great deal of education needs to be done on the subject before people are willing to accept this technology in their backyard. People would be comfortable living around such a reactor. The environmental impacts of lifter reactors are also minimal, as they don't produce large amounts of heated water to dump into the ecosystem. And as I already mentioned, the spent fuel is quite safe compared to current nuclear reactors. Other countries have less problems with nuclear stigma, and China and India are both making great strides towards using this technology to boost their own economies. China, for example, plans for 10% of their power to be nuclear-based by 2030 and 18% to 2060, and a large amount of this production would be thorium technology.
All right. So looking back on our project after we all came together and finished our various power production technologies and researching them, we decided to reflect on what we learned and what we could do differently next time. And one of the biggest things that we all agreed on was that the weight of different categories greatly affects the outcome. And so in some ways, the weight is somewhat arbitrary. And the categories themselves are also broad. And so assigning values and pass/no pass grades to the criterion is quite difficult. And so one of the reasons that the weight is partially arbitrary is that, like, take sustainability for example. We had it weighed high, as arguably it should be, but under sustainability it's like there's categories like how much does this pollute the surrounding waters, how much does this increased CO2 or methane levels in the atmosphere. And so like one of the issues is that it's difficult to like these are all under the same category. And how can you we're basically saying that those are equivalent and that their negative impacts are equivalent when we put them under the same category. So further discerning the categories would be one of the biggest things we would do. And so one of our other concerns is the resource acquisition at the start of manufacturing. And also the biggest hurdle when considering any project is the initial investment, which can be very high in each of our cases. And so the mining of resources has become famous by like the whole cobalt mining in Africa. In impoverished areas in Africa, it's famous for human rights violations. And so these human impact concerns affect every project, and so they cannot be individually, so they have to be individually examined. And it's also quite difficult to tell, looking at a finished product, what all it went through to get there. And foreign companies often use mines and do not have local populations' health, mental and physical in mind. And so these abuses can stack into a staggering toll on human life overall. So it's just something to consider when thinking about one of these engineering ventures.
That's so true, guys. And now basically this is our table of results, where we have the level of importance down here, and then the rating that we each gave to our individual energy sources. And based on these, the max score of 53, thorium won out over the other two by 0.6. And so that is the one that we would have to recommend going into the future. And that about wraps it up, I believe. Does anyone else have anything they would like to add?
No, I think we're good.
All right.
Yeah, I think we're good. All right, I'll stop it here.